This time, let's take a look at limits. Last time we set the stage by calculating the area of a circle of radius r using polygons. In particular, we noticed that the apothem, that thing that went from the center of the circle to the midpoint of the opposite side, that approached the radius of the circle. And you might remember we looked at it for 3, 4, 5, 6, 7, 8, 9, and 10 sides. As n gets really big, we see visually that h approaches r. And for simplicity, let's just say that the radius is 1. In the circle of radius 1, that gave us this triangle, and h was cosine pi over n. And then we saw algebraically, if h is cosine pi over n, as n gets really big, pi over n gets small, it goes to 0, and as pi over n goes to 0, cosine of pi over n goes to 1, and so h, which is cosine pi over n, also goes to 1. We could also look at the graph of y equals r cos pi over x, and that looks something like this. If we also draw the line y equals 1 in there, we see that as x gets bigger, cos pi over x gets close to 1. We can expand our range and see that more clearly. Now, more formally, what we say is that the limit as x goes to infinity of the cosine of pi over x is 1. And by as x goes to infinity, we don't mean that x is getting close to infinity. We just mean that x is getting arbitrarily large. In other words, as x gets really, really big. Formally on the graph, we mean this. You tell me how close to 1 you want to be. That's a number, say, epsilon, and I'll draw dotted lines to say, okay, here we are within epsilon of that y equals 1 line. And once you've chosen how close you want to be, I choose that vertical line and say anything to the right of there is that close. The graph of y equals cosine pi over x is never outside of that range. In math, we say this in symbols that say you choose any epsilon, and for any epsilon, there's some n, so that if x is bigger than that n, then the distance from the cosine of pi over x to 1 is smaller than that epsilon you chose. You choose the orange dotted lines. I get to choose the blue line, so that to the right of that line, my graph is always within the range of the limit. Looking at that same graph, you might notice that as x gets close to 0, there is no limit. Now we're only looking at values of x greater than 0 here, so we write that as the limit as x goes to 0 from above of the cosine of pi over x, and what would that limit be? And as you move closer to x from the right, you see that it wiggles faster and faster and faster so that there is no possible limit. For example, say we choose y equals 0 as the limit, and we draw this epsilon range around y equals 0. There's no value where we stay in that range. So there is no limit. The limit as x goes to 0 from above of the cosine of pi over x doesn't exist. On the other hand, we started this discussion by looking at these polygons, and we looked at values of n, and we said as n gets bigger, n is 3, then 4, then 5, then 6, the limit of the cosine of pi over n, and then we kind of drew a graph where we weren't worried about just integers anymore. So let's let x be 1 over n. And so as n gets really big, x goes to 0 from above, and so we can say the limit as x goes to 0 from above of the cosine of pi x is 1. And if we draw the graph, we can see this, and we play that same game we played before. You choose any epsilon, any small number, and I look above and below my limit by the amount epsilon, and we should be able to find some value of x so that anything to the left of that value stays within that limit. The graph stays within epsilon of our limit 1. And we write this formula as saying for every epsilon, there exists a delta, because we're thinking of a small value of x this time, such that if my x is positive, but it's still less than delta, that the value of cosine pi x is within epsilon of 1. And we see that here. You choose your small epsilon, I get to find a delta to the left of that delta, but greater than 0. Cosine of pi x stays within that limit. And that's a first formal exploration of limits.